I heard that's what nowadays what people talk a lot about the AI systems, right? And at the end of the day, we can find that for a lot of AI database AI systems or agentic AI are essentially built on top of the database systems, and they actually need the data from the data systems, right? And so that's why I feel that's why it's always very exciting to just talk about the core technology, right? Well, how we build the database systems. So if you have never heard about RisingWave, then that just will give you one single slide page. So RisingWave is a distributed SQL streaming database system. So what it means, what is a streaming database system? There are two ways to think about that. One is that, okay, basically we can process streaming data, like IoT data, like financial service, like stock market data, like energy data, right? Well, all this kind of data, like streaming data, you can process. There are two ways to understand what a streaming database is. The first one is that we can essentially process the streaming data in a database way, that is using just a SQL. And the second way to understand it is that, okay, we can essentially using database system to process the streaming data. Okay, and the RisingWave's goal is to provide the users with the best-in-class stream processing management and analytics systems. Imagine that where you have, let's say, Kafka streams, or you have a Postgres CDC, you can ingest basically using RisingWave to ingest the data directly from the data sources. And the RisingWave will handle the processing, basically transformation, joins, analytics, whatever. And then it can either directly store the data and serve your online applications, or sync data into downstreaming systems. And more recently, we also added the native Iceberg support, which means that you can basically have hosted Iceberg inside of RisingWave. Basically, you can use Iceberg using Postgres style SQL to manage everything inside of Iceberg. Yeah, this is another slide. Well, I mean, RisingWave is an open source project, and it's under Apache 2.0 license, and we have been adopted over 1,000. I think it's definitely more than 1,000, probably 2,000. Yeah, we never counted, but yeah, we have a lot of customers from the startups to Fortune 500 to Fortune 500 enterprises. In Germany, we have customers like Siemens, like Henkel, like many others. And these days, we also see more and more customers are moving from batch to streaming. So, for example, the financial services, right? If you think about payment services, well, I mean, they definitely want to detect the fraud in seconds, and actually sub-seconds. We are essentially powering the leading payment service credit card company called Ramp in the U.S., which is essentially I guess it's probably the #1 corporate credit card company in the U.S. And they use RisingWave to detect fraud. And in capital markets, well, definitely everyone wants to use stream processing in order to find signals, right? So that's where we can find the alpha. And the capital markets company, Wall Street companies using RisingWave as the order management systems, or probably they want to do the per-trade analytics, post-trade analytics, whatever. And for entertainment, there are gaming, sports betting, publishers, and in e-commerce, okay, personalized recommendation, price comparison, and many others, right? And for energy and manufacturing, right? Well, people talk about okay, I have the IoT data from my factories. I want to collect all this data and then analyze this data in real time and then take actions if needed, right? So logistics is another very interesting use case we found for stream processing. So yeah, that's about RisingWave. And if you want to compare RisingWave with any other systems, I can tell you that actually, essentially around 60% of our users compare RisingWave with Flink, and probably around 20 compare RisingWave with Spark Streaming. And some other people compare us with, let's say, just a Postgres, right? Postgres materialized use, or OLAP databases, right? Because we know that there are a lot of OLAP databases, and they all claim that they can process streaming data. But we process streaming data in an incremental way, which is totally different from the other database systems. And for some other people also compare us with time search databases. But anyways, I think we are pretty unique in this industry. So today I will not talk too much about how we are different from all the other systems, right? And I just want to tell you something about our design principles. We only have 2 design principles. The first one is ease of use, and second one is cost efficiency. For ease of use, I probably will not spend too much time talking about for ease of use because, well, as long as you check our documentation, you know how easy it is. But we always are very proud of our user experience because we are basically Postgres compatible, and everyone loves Postgres, and everyone knows how to use Postgres. You can essentially use RisingWave in the same way as using Postgres. Just imagine that, you want to do some stream processing over, let's say, customer data, right? You do not need to write something like Java code and write a Java library and upload it into some systems. The only way you need to do is to create a materialized view. That's it, right? And the Postgres, why Postgres is so interesting? Because Postgres really has a super good ecosystem, and you can, as long as you have systems that can connect to Postgres, you can use this system to connect to RisingWave. This is more advanced topic, but if you have ever used any stream processing system, you will know that these stream processing systems always require state management. Because they use something like a RocksDB to manage the internal states. We just basically hide the details from the customers, from the end users, so that they do not need to care about the details. And about the simplified data stack, I think I can directly skip this part. So then let's talk about I think it's more interesting part, which is the cost efficiency. So for cost efficiency, what does it mean when we talk about the cost efficiency? Essentially, it means 3 things: runtime performance, failure recovery, and dynamic scaling. For runtime performance, it's pretty simple to understand, right? Let's say that we want to process data streams and how fast it could be, right? Or how low the latency could be, right? And for failure recovery, it means that, essentially, what if my system failed? If my system failed, I really want to recover from the failures just in seconds, not in hours, not in days. Impossible, right? But I don't really want to have my system to crash to be done in, let's say, for hours. It's not quite tolerable. And then talk about the dynamic scaling. What it means that, for streaming workloads, we always have the fluctuations, right? We really want to be reactive to fluctuations, and we really want to scale in and out in seconds in order to cut cost and in order to adapt to the workload, right? So how can we achieve all of these 3 points? Well, we used architecture, which is super popular, called S3 as the primary storage architecture. If you never heard of this term, then I can tell you that you can just think about, storing all the data in S3, the AWS S3, or any S3 compatible system like Google storage, or probably Azure Blob storage, right? Or probably some other any system that is compatible with S3, right? You can store all the data in S3, and then do the compilation in your compute node like EC2. So that's where every time you want to scale in and scale out, you can just scale in and out the compute and storage independently without worrying about whether we need to shard the data or whatever, right? So definitely there are some other names like decoupled compute storage architecture, or shared storage architecture, or tier storage architecture, whatever. And all this, I think this architecture is really popular, and leading companies like Snowflake, I'm not sure about the database architecture nowadays, but definitely Snowflake uses, and I think ClickHouse will use some tier storage architecture, And RisingWave is probably the only system that adopts the S3 as the primary storage architecture for powering the stream processing, which is pretty unique, and I will talk about the pain point later. So this is a pretty straightforward comparison between Flink architecture and RisingWave architecture. So Flink was a stream processing system that was invented around probably more than 10 years ago. And the architecture is pretty simple. As long as you understand Hadoop, you understand how it works. Basically, in the system, in a stream processing system, you actually have to manage the states. What Flink does is that, well, okay, if I want to scale out from one system into 3 different systems, then I can just partition the state into 3 pieces, right? Okay, state 1, state 2, state 3, and then so that every time a new event comes in, it will be shuffled to one of the machines. And the compute node only need to take care of a local state, right? So that's okay. Yeah, the workload is basically sharded. But in RisingWave, the architecture is totally different. The way we do it is that, okay, we basically store the entire state in S3. And if we want to scale out from one machine to 3 different machines, then we do not really do sharding. We basically scale out to 3 different machines, right? But it doesn't really mean that, okay, state is not sharded. The state is sharded in multiple slices. But so that's what the compute nodes can select, okay, which states they want to load at the runtime. So this is the difference between the Flink architecture and the RisingWave architecture. So there are several benefits of this decoupling S3 as the primary storage architecture. The first one is failure recovery. Let's imagine that, okay, what if the compute node failed, right? Because it is computer, right? Well, and it's quite possible that one of the nodes failed, right? So in Flink, if you understand Hadoop, well, how it works is that, well, whenever we have a machine that crashed, we will basically boot a new machine and ask a new machine to reload from the checkpoint and reload the state from the checkpoint. So that after reloading, we can continue running, right? Okay, this is pretty simple. It looks pretty simple, right? And what's the pain point? The pain point here is that what if the state is pretty large, right? Imagine that you are joining multiple tables, right? If you are joining multiple tables, then the state can be pretty large. Let's say 100 gigabytes or probably 1 terabyte. It's possible, actually. So if we have such kind of large state, then reloading from S3 can take essentially hours. So which means that the system will be down for hours after crash, right? Well, this is the very traditional architecture. In RisingWave, we take a very different approach. That is, we directly store everything in the S3. And then every time a new machine crashed, we do not need to recover from the failures. We do not need to reload the state from the S3. Why? Because, well, remember that every single machine is basically stateless, and all they stored is basically a cache. If the cache crashed, well, okay, doesn't really matter, right? We can just reload from the S3, right? And the cache can be reloaded at a runtime, right? We do not need to populate the cache beforehand, right? So once the system crashed, in order to recover from the failure, the only thing we need to do is to boot a new machine and tell the new machine, okay, look, the data is stored in S3, and reload from there. And the system can just keep running without waiting for the system to reload. That's how we handle the recovery. Okay. So for dynamic scaling, well, because of time constraints, well, I want to be quick. So for dynamic scaling, well, it's very similar. In order to scale from one machine to 3 different machines, if you use Hadoop-like architecture, then what you need to do is to basically shard this state to 3 different pieces and then scale out. It will take time if the state is big. But in our case, well, in RisingWave architecture, we do not need to do that. Well, you can just boot 3 new machines and tell the 3 new machines that where the state is, and the three new machines will basically reload at the runtime. So it sounds very simple to implement this architecture, right? But I have to say that, well, I mean, you actually you will never run into any issues until you just implement this architecture. Well, the main pain point of this architecture is that definitely performance and the cost. In terms of performance, what's the pain point? What's the problem of this? Well, the problem here is that S3 access represents the most significant bottleneck, performance bottleneck. And every time we access S3 is super slow, and S3 will bring in, let's say, 200 to 300 millisecond latency. If you want to do stream processing, which means that you want to be super fast, right? Well, let's say sub-second latency, right? If you want to do stream processing, then every time we access S3, it will incur 200 and 300 millisecond latency. You know that's why it's not tolerable, right? Well, it's definitely not very good for streaming. And in the meanwhile, it's not just about a 200 and 300 millisecond latency. In the meanwhile, cost is also a big problem. People may be very surprised why storing data in S3 can be a problem in terms of cost. Well, S3 is super cheap. I agree. Yeah, it's $23 per terabyte per month. But don't forget that after paying for the S3 storage, you also need to pay for the S3 access. And the S3 access could be extremely expensive. And in some of the workloads, well, it can account for 50% of the cost if not optimized efficiently. Why? Because, well, S3, AWS does not really only charge you for the storage. It also charges you for the access. Every time you access the S3, you will be charged, right? Imagine that for stream processing use case, imagine that every single second, if we access the data for, let's say, S3 for 1,000 times, then how much you need to pay? You probably need to pay, 0.5 cents, right? But remember that that's just for 1 single second. So how much money you need to pay for 1 hour, right? Well, and how much money you need to pay for one month? It will be a huge cost if you accumulate all of these costs together. So if you want to adopt the S3-based architecture, I agree that you will definitely get a lesser scaling, you will definitely get an instant failure recovery, but cost and performance can be a huge problem. Then how do we solve this problem? Well, we solve the problem by, the idea is pretty simple. That is, just increase the cache. Just add the cache in the local machine. Then, but for cache, there are a lot of detail to discuss, right? What kind of cache we want to add into a local machine? Do we just add a local SSD or what? So we can essentially add a local SSD, and if you talk to a lot of database vendors, they probably will also tell you that we can just add a local SSD. But what I can tell you is that adding local SSD might not be, it could be the best solution, but it might not be the best solution. Why? Because local SSD is actually pretty expensive. In AWS, if you launch a machine with local SSD, NVMe SSD I'm talking about, if you launch a machine with local NVMe SSD, it will be around 25% more expensive compared to the machine without a local SSD. So that's a trick. So if you imagine that, if you boot 20% or 25%, you may think that, probably it's just a small amount of money, right? But imagine that, what if you launch, let's say, 100 machines or probably 1,000 machines? It will be a huge amount of money. And that's a problem. Local SSD could be very expensive. And another challenge here is that, for the disk specs in different cloud providers can be hugely different. So if you have running a system, no matter whether it's RisingWave or probably ClickHouse or whatever systems you are running, It could be a problem if you want to run a system in multiple clouds, right? Because well, disk space can be very different. Then what's our solution? Our solution is that, okay, let's just use the cloud native solution that is, well, I mean, in the best, it's EBS, Elastic Blob Services. And the performance is actually good enough. I can provide the numbers later. The performance is actually pretty good, and the cost is reasonable, and it's actually lower, comparatively lower than local SSD. So, but definitely this is just a hardware, right? And we also want to add a software to do the caching. So how do we do that? Okay, so we actually build a system, caching layer called Foyer. Foyer is a hybrid cache building Rust. And Foyer's goal is to be efficient and user-friendly hybrid cache library. It's not a system. It's just a library. It's just a library and building Rust. So that's why, as long as you are using Rust, you can essentially embed Foyer into your system. So that's where you can cache the data from S3 in your local either local disk or probably in your, let's say, even in your memory, right? Yeah, this is the very simplified architecture, right? Let's say that we do some computation. Here, it's a hash aggregation. If we want to do some hash aggregations in here, instead of just storing data in S3, we can essentially cache huge amount of data in the local disk as well as the memory. So there are several, building Foyer is not that easy because there are a lot of details to discuss. First, for example, for the whenever we build a cache, we probably need to think about what the caching policy, right? We actually have a plug-and-play algorithm to ensure that it's easy for the users to choose their own caching algorithms. And for the caching system, another trick here I want to tell you is that you definitely want to make sure that it's highly concurrent, because you have to understand that you probably have multiple threads or multiple users to access the cache at the same time, right? So you definitely want to make sure that it can enable highly concurrent access, right? And there are some other details, and I will skip this part in this talk. So here's the performance results we did. So on the left-hand side, we show the S3 read without the disk cache, and on the right-hand side, we show the S3 read with the disk cache. So the lower the better, right? We actually want to eliminate the S3 read, right? But the lower the better. So you can see that once we enable this cache, we can essentially drop the S3 access from around, let's say, on the peak, it's probably around 800 megabyte per second to just 75 megabytes per second. It basically dropped the access by 90%. And similarly, we also dropped the S3 cost. In the past, if we without get this cache, we actually this is around 8 hours, right? Well, it's probably 8 hours. We actually need to pay $20 for the S3. But after enabling this cache, we can drop the price we can drop the cost from $20 to just $3. So it also reduces your S3 access cost by 90%, which is a huge saving. And performance-wise, we can also see that performance-wise, the higher the better. We can see that once we enable this cache, we can get a better performance because we do not really need to access S3 so frequently, and it definitely reduces the S3 access latency. So the title, the talk title is about how we can achieve 100 millisecond latency, right? Well. Once you adopt all these tricks for the caching mechanisms and the EBS or whatever, you can probably achieve sub-second latency. But how you can achieve sub-100 millisecond latency? Well, I just want to use one single slide to summarize what we did. The first one is that you definitely want to have strict 0% cache miss. That is, you don't really want to access S3 at all. So you definitely want to make sure that all the data is cached in local machine, either in your local memory or in your local disk. Because why? Because any cache miss could cause high latency, larger than 1 second. And the second trick we played is that we actually use the machines with larger memory, with a larger CPU versus DRAM ratio. That's the second trick. And the third trick is that we actually optimize the execution performance a lot by using larger data chunks and using simple instructions. Putting all this together, we can achieve 100 millisecond latency in stream processing, even with an S3-based architecture. Okay, here's a summary. RisingWave is one of the very few stream processing systems. It's probably, if it's not the first one. I think, but I believe that's why it's definitely one of the very few stream processing systems that can achieve sub-100 millisecond latency. And it adopts a decoupled computer storage architecture with a smart caching layer. And the third thing here that I want to, in the summary, is that the devil is always in the details. And after you implement this structure, you will definitely come from a lot of challenges. And for all these challenges, probably need to take Mondays and fix these issues. And the vibe coding doesn't really work, I guarantee you. Yeah. Okay, thanks. That's all my talk. If you are interested in RisingWave or interested in data engineering, feel free to join our Slack community. All right, thanks.